In this section, we'll take a look at line integrals. And again, I'll point you to the PowerPoint for an introduction as to what a line integral is. But what you're basically doing, I put this one picture up here that I took from the textbook, is that you're looking at a portion of the surface with some curve, right? That red curve is placed on that surface. And if you think of taking the area from that curve and dropping a curtain in front, that's what you're finding the area of when you do a line integral. So you're finding the integral with respect to the area under that curve of some function with respect to s. So we'll start this way, and then we'll move on to what happens if we have other parameters besides that. All right, so these line integrals are calculated using parameters. So I want to find the integral over some curve of x plus y, where c is the unit circle. So the first thing I'm going to do is I'm going to write the equation for that circle in parametric form. All right, so that circle is x squared plus y squared equals 1, which means that if I write it in parametric form, s is equal to the cosine of some parameter s, and y is equal to the sine of some parameter s. And this is true for s values from 0 to 2 pi. Right? If I go from 0 to 2 pi, I'll have completed that unit circle. All right, so now when I go and I look at my integral, it's the integral of x plus y. So it becomes the integral of cosine of s plus the sine of s integrated with respect to s from 0 to 2 pi. All right, so the antiderivative of cosine is sine, and the antiderivative of sine is negative cosine. And we're now going to evaluate this at 2 pi and at 0. So I'll come down here, I'll get the sine of 2 pi minus the cosine of 2 pi, right? So that's upper limit of integration. On the bottom, I'll get the sine of 0 minus the cosine of 0. So the sine of 2 pi is 0, the cosine of 2 pi is 1, sine of 0 is 0, and the cosine of 0 is 1. So I end up with negative 1 plus 1, which is 0. So the value of that line integral is 0, and wouldn't it be great if they were all that easy? You notice something interesting when we did this calculation is that s was not only the angle measure, but it was also the arc length. So in this case, the arc length was a parameter. We went from 0 to 2 pi on the angles, which in this case were the s's. So going from 0 to 2 pi on the s's also was the length of that unit circle. Not always going to be the case, right? If you go from 0 to 2 pi on a function, doesn't mean the function is always 2 pi units long. In fact, it'll happen on the unit circle and not everywhere else. So setting up parameters. What if the parameter is not based on arc length? Then you got to find the arc length. Replace the ds with the arc length. And so now, for that vector, the arc length is the integral of the derivative. Well, when you take the derivative of both sides, you realize that your ds is basically r prime of t. So we didn't have to do that before because our r prime of t was just 1, right? The magnitude of the radius of that unit circle was 1. Now we're going to have to look at the functions a little bit more critically to see if, in fact, arc length is a parameter or not. And if it's not, which most of the times it will not be, you're going to have to add that magnitude of r prime as your ds to convert them. All right, so suppose I've got this function, the integral of xy to the 1/3, and notice it's integrated with respect to x, or s rather, where that curve is a parabola with x values from 0 to 1. So I'll try to use t's for this. S's are kind of cumbersome, plus we want to make that difference between it, arc length being a parameter and not a parameter. How do I set this up, this curve, in parametric form? Well, the easiest thing I think is just to let x be t, and then your y is t squared, because if y is equal to x squared, whatever I pick out for x, square it, and you got y. This now works for t values from 0 to 1. But the distance from 0 to 1 is not 1, so I'm going to have to set up my parameters. So now let's set up a magnitude of r prime. Okay, how do I set up my magnitude of r prime? Well, it's going to be the square root of x prime of t plus y prime of t squared, right? So it's going to be the square root of x prime squared plus y prime squared. Well, x is equal to t, so x prime is just 1. Y is equal to t squared, so the derivative of t squared is 2t. And remember, it's each of these things squared. So, well, 1 squared is just 1. So this magnitude of r prime will give me the square root of 1 plus 4t squared. That's my ds. All right, so what are my new limits of integration? Well, my new limits of integration are the t values. The t values go from 0 to 1, so here we're step 3 limits of integration. They still go from 0 to 1. Now, substitute everything back into the original. So I have the integral of xy to the 1/3 integrated with respect to s. So this now becomes the integral of xy to the 1/3 integrated with respect to s becomes the integral of t, right, because that's my x, times t squared, because that's my y, to the 1/3. The ds is still sitting over here. The ds is the square root of 1 plus 4t squared. I'm integrating with respect to t from 0 to 1. And now I'm going to rely on previous techniques learned in other courses to finish this off. This becomes the integral from 0 to 1. T times t squared is t to the 3rd. T to the 3rd to the 1/3 is just t. So I get t squared of 1 plus 4t squared. And maybe this is worth going all the way through as a nice little reminder of u substitution. All right, this time we'll let u be what's under the radical, 1 plus 4t squared. Therefore, du is going to be 8t dt. Well, I don't need 8t, I just need 1t dt, right? Because here's my t, here's my dt. So let's multiply by an eighth. 1/8 du equals t dt. The other thing that I have to do is reevaluate those limits of integration. So my limits of integration in terms of t are 0 to 1. Well, what are they now in terms of u? U evaluated at 1 and u evaluated at 0 are my new limits of integration. So when I put a 1 in here, I get 5, right? 4 times 1 is 4, plus 1 is 5. When I put a 0 in there, I get a 1. All right, so this gives me the integral from 0 to 1. I'm sorry, from 1 to 5, new limits of integration. 1 to 5 of 1/8 dt, that 1/8 du, that takes care of my t dt. And then under the radical goes the square root of u, right? So I've got now 1/8, the integral from 1 to 5 of u to the 1/2 du. Add 1, divide by the new power, so now I get u to the 3/2 divided by 3/2, but instead of dividing by 3/2, I'll multiply by 2/3. And I'm going to evaluate this at 5 and at 1. So first of all, this becomes 1/12. And then I get 5 to the 3/2 minus 1. Right? 1 to the 3/2 is just 1. I suppose I could leave it like that. I could also clean it up a little bit and write it as, what, 5 square root of 5. That's 5 to the 3/2 minus 1 all over 12. So that's the value of my line integral. If you want a little recap, let's zoom out and see what we did over here. I took the original function that was given integrated with respect to s. My curve did not have an arc length that was equal to the parameters, so I had to reevaluate that. So I set it up in terms of t, let the t's go from 0 to 1, and that gave me the same length there. Then I had to find the magnitude of r prime that essentially replaced the ds, and then set it up with the integral, replace the x and the y with their equivalents in terms of t. Don't forget your magnitude of r prime. That takes care of the fact that the arc length is not a parameter. And then evaluate. In the process of evaluating, that's where I introduce the u substitution. You won't always need a u substitution, but you might. In that case, that's how you do it. So we go eventually back to Calc 1 and 2 techniques to finish evaluating it. All right, take a look at this. I'm going to start this off. I don't know if I'm going to run through the whole thing. I want to evaluate that integral, xy over z, integrated with respect to s, except this time it's over a line segment with two endpoints. Endpoints are 1, 4, 1 and 3, 6, 3. What do I need first? Well, the first thing I need is I need the equation for that line segment in parametric form. All right, so if my endpoints are 1, 4, 1 and 3, 6, 3. So it starts at 1, 4, 1 and it goes to 3, 6, 3. I need a direction vector. How do I get from the first point to the second point? Well, I'm going 2 to the right, I'm going 2 to the right, and I'm going 2 to the right. So if I take a direction vector to go from the first point to the second point, my direction vector would be 2, 2, 2. All right, so now I need to set up that r sub 0 plus vt. So my r sub 0 is 1, 4, 1 plus t times 2, 2, 2. That makes the x equal to what? 1 plus 2t. The y is equal to 4 plus 2t. And the z is also equal to 1 plus 2t. And this is for t values between 0 and 1. If I'm in doubt, put a 0 in for all these t's and I get 1, 4, 1. Put a 1 in and I get 3, 6, 3. All right. Then I need the magnitude of r prime. So the magnitude of r prime derive 1 plus 2t and I get 2. So it's going to be 2 squared. And now can you see where this is going? They're all going to be 2's. 2 squared plus 2 squared plus 2 squared, 4, 8, 12. Square root of 12 simplifies to 2 root 3. Right, and now when I set this up, it's the integral of xy divided by z. So the integral of x, which is 1 plus 2t, times y, which is 4 plus 2t. So there's xy divided by z. Don't forget to multiply by the magnitude of r prime, integrated with respect to t, from 0 to 1. So look at all those things I had to remember. I have x, y over z. There's my magnitude of r prime and my limits of integration. Well, this thing works out nicely and the 1 plus 2t cancels here. So this just gives me 2 radical 3, integral from 0 to 1 of 4 plus 2t. All right, so I get a 4t plus t squared. Evaluating it at 0 gives me nothing, so evaluating it at 1 gives me 4 plus 1, which is 5. 5 times 2 square root of 3 is 10 square root of 3. And there's my answer. All right, let's try another one. This time we'll take a look at length of a curve. Remember there was a formula in Calc 2 for length of a curve, the square root of 1 plus dy dx squared. Well, you can use line integrals to find the length of a curve by letting the function simply be equal to 1. And so you're really then integrating the magnitude of r prime. So suppose I have this curve, 30 sine t, 40 sine t, 50 cosine t. I think it's a nice spiral if you want to go on to Desmos or Mathematica and graph it. How do I find the magnitude of r prime? Well, the magnitude of r prime is, first thing I need r prime. So the derivative of sine gives me cosine. The derivative of sine gives me cosine. And the derivative of cosine gives me negative sine. So now the magnitude of r prime is going to be the square root of the first term squared. So 30 squared is 900. so 900 cosine squared t, then 1600 cosine squared t, and then when I square a negative, I get a positive, so plus 2500 sine squared t. Oh, look how nice this works out. This gives me 2500 cosine squared t and 2500 sine squared t. Well, a Pythagorean identity will get us sine squared plus cosine squared is 1, so it just gives us the square root of 2500, which is 50, right? The square root of 25 is 5. The square root of 100 is 10. 5 times 10 is 50. And so now, all that's left is for me to integrate from 0 to 2 pi of the magnitude of r prime with respect to t. So this gives me 50 times 2 pi minus 50 times 0, 100 pi. All right, so that's what we did. We essentially set it up as 1 times the magnitude of r prime, 1 times the magnitude of r prime, integrate it, you end up with 100 pi. All right, the PowerPoint runs through a couple of different ways that we get these line integrals of vector fields written in alternate forms, and eventually they all make their way to this set of formulas. The one on the top and the one on the bottom actually lead us to a formula that you're going to see over and over and over in these few sections, which is f dot dr. A lot of these line integral formulas of multiple variables can all be reduced to the integral of the dot product of the vector field and the derivative of the parametrization. So it could be r as x and y of t, it could be r as x, y, and z of t. This one's given in three-dimensional form, right, x, y, and z. So r is my function that I'm setting up the parameters for, and then the vector field is given, and I do the dot product, and I integrate, which means there's going to be a lot of t's, a lot of parameters set up. They did the same thing down the bottom. They took the dot product of these two vectors and showed that you actually end up with the same thing, the dot product of f and dr. f dr, that's what we're integrating. All right, so this one is missing its dot. Okay, so evaluate the dot product of f and t, where f is a vector field that's negative yx, and the semicircle for cosine t for sine t has t values between 0 and pi. All right, so what do? Well, the first thing is we already have our r, right? This is our r of t, so we need an r prime. R prime will be the derivative of cosine, so negative 4 sine t, the derivative of sine, so 4 cosine t. And now I'm going to take the dot product of f and dr. So f is given over here, right? Negative yx. And I'm going to do the dot product of that and r prime. So I get negative yx dot. The r prime we came up with was negative 4 sine t, 4 cosine t. But wait a minute, we can actually replace those y's and x's with functions of sine. If it was given to us that the r function was 4 cosine t, 4 sine t, that's actually my x and that's my y. So let's replace the y in here with a 4 sine t. So I get negative 4 sine t, and I can replace the x with a 4 cosine t. Dot what I originally had, negative 4 sine t, 4 cosine t. So when I set this up, that's my f, that's my dr, and now I need the dot product. So the dot product will give me positive 16 sine squared t plus 16 cosine squared t, and then I'm going to integrate this from 0 to pi. Well, look how nicely this works out, right? Sine squared plus cosine squared is 1, so I'm actually just integrating from 0 to pi of 16 dt, which gives me 16 pi. All right, take a look at the other example here because it's a little bit more complicated. This says integrate the dot product of f and t for f equals xy over square root of x squared plus y squared on the line t for t for t values between 1 and 10. So we already have r of t, right? This is our r, which actually makes r prime pretty easy because the derivative of t is 1, the derivative of 4t is just 4. So now I need to substitute that into my vector field. So I replace the x and the y with a t and a 4t. And on the bottom, I get x terms squared plus y terms squared. So this gives me t 4t on the top and a 17t squared on the bottom. So I can actually write this as my field being what? 1 over 17t, 4 over 17t. Now I need to take the dot product of that and 1 and 4. So I need to take the dot product of 1 over 17t. No, the t goes in the bottom. 1 over 17t and 4 over 17t dot r prime. All right, so there's my FDR, and I'm going to evaluate this from 1 to 10 because that's what the original problem asked me to do. So this will give me 1 times 1 over 17t, so 1 over 17t, plus 16 over 17t. Oh, how nice. Look at that. I get 17 over 17t, which is 1 over t. So now all I have to do is integrate from 1 to 10 of 1 over t dt. That gives me the natural log of t, evaluated at 10 and at 1. So I get the natural log of 10. Natural log of 1 is just 0. So there's my answer. All right, so a little recap of what we did over here. Both of these were done by using the FDR formula. We want to evaluate that dot product, and FDR is the way to do it. So we already given our function for r of t, we found r prime. We took the x and y values in terms of t and substituted it into our vector field, and then took the dot product of the vector field and r prime, except we wrote the vector field in terms of t so that everything would be in terms of the same parameter, and then evaluate it. All right, we'll take a look at circulation and flux in the next video.